Assalamualaikum and good evening. So today I would like to share you a few example to calculate the drag and lift force because previously we learned the application of the boundary layer and finally we learned about the lift force and drag force that generated by airfoil. So in example 1 here, a rectangular wing on a small airplane has a 1.3 meter chord and a 10-meter span. They're flying in air. When flying in air at 220 kilometers per hour, the wing experiences a total aerodynamic force of 18 kilonewton. If the lift to drag ratio is 3, so determine the lift coefficient of the wing. So we know in our first introduction of the chapter 6 here, we know that if we have an airfoil like this one, so actually we could divide into two basic component force, which is the lift force and the drag force here. So and then we could say that the total aerodynamic force here is 18 kilonewton, can be written as the total force, which include the lift force here and the drag force here. So we could have this term, and then in this question, it gives that the lift to drag ratio is 3. So means that the ratio between lift force and the drag force is can be written is like this one. So we, by using these two equation, so we could have this term. So we have 9fd square plus fd square equal 324, and then we could determine that the lift force is 17.1 kilonewton. So and then the relationship between lift force and the lift coefficient can be written like this one. So normally in textbook we will write as lift force, it is equal to CL times 1 over 2 rho AV square. So and then we could determine the lift coefficient. CL here is equal to 0.587. So this is the example 2. In a lift and drag experiment performed in a wind tunnel, a NACA 0012, airfoil was used. The airfoil has a 15 centimeter chord and a span length of 45 centimeters. Using a force measuring device, a lift force of 60 Newton was measured on the airfoil for a Reynolds number of 4.586 times 10 by the power of 5. The lift coefficient for this airfoil is given by CL 2 pi sine alpha, where alpha is the angle of attack under the given condition. So what is the angle of attack in degree? So this is the common diagram relationship between the angle of attack and also the lift coefficient here. And so we have, this is the NACA 2414 airfoil, and this is the NACA 0012 for this question. So this is the curve that created by the these two airfoils. From the question, we know that the Reynolds number is 4.586 times 10 by the power of 5, and then we could equate with this equation, the equation for the Reynolds number, rho VL over mu. So, and then we could get the velocity is 45 meter per second. So, and then from the question, it says that CL, the coefficient of lift, is equal to pi sine alpha. So, and then another equation for CL here can be written as FL over 1 over 2 rho AV square. We know the value of V is 45 meter per second. And then we know the lift force here from the question, which is 60 Newton here. So, and then we could calculate the value of alpha here, which is equal to 6.52 degree. So in example 3 here, an aircraft with a mass including payload of 1,000 kilogram is designed to cruise at a speed of 80 meters per second at height of 10 kilometers. The effective wing area is approximately 15 meters square. determine the lift coefficient and the angle of attack. What power is required by the airfoil during cruise? So assume a conventional airfoil. So the lift coefficient, the equation is CL equal FL over 1 over 2 rho AB square. So we substitute everything in the equation. So we could get the coefficient of lift is 0.496. So and then because we use the conventional airfoil, so we could assume that we could get the angle of attack here. So it is equal to 2 pi sine alpha as stated in the previous question. So we could equalize with 0.496. Then we could get the alpha here. The angle of attack is around 4.53 degree. So and then the drag coefficient for the conventional airfoil is 0.0065. So this is the common assumption if we talk about the conventional airfoil. And then we could calculate the power. So rumus, the equation for the power is FD drag force times velocity. So we could calculate the drag force here by using this equation. CD is the coefficient of drag times 1 over 2 rho AB square, and then we time with the velocity here stated in the question as 80 meter per second. So we get it is around 10,300 watt. So in example 4, a 1500 kilogram aircraft is designed to carry a payload of 3000 Newton when cruising at 80 meter per second at a height 10 kilometers. The effective wing area is 20 meters square, assuming a conventional airfoil. Calculate the takeoff speed if an angle of attack of 10 degrees is desired, the stall speed when landing, the power required at cruise if 45% of the power is needed to move the airfoil. So for the takeoff speed, we know that, so this is the lift coefficient that usually occur at the takeoff speed. So we take as CL is equal 1.22. So it is equal to FL over 1 over 2 rho AB square. And we calculate everything here. So and then because we have a payload at 3000 here, so we add with the total weight. So we have a 1,500 kilograms, and then we have 3,000 newtons. So 1,500 we times with the gravity to get the weight, and then we add another 3,000, the load of an extra load for the flight. So and then we calculate everything. So we could get the velocity is 34.5 meter per second. And then to calculate the stall speed here. So again, so we take the CL is 1.72. So this is the common value of CL when we calculate the stall speed, because we are using the conventional airfoil. So this is the equation for the lift coefficient, and then we substitute all the value here. So and then here the difference is the value of the density, the rho of the air. So for the takeoff speed, so the air is at the sea level, so we take 1.23 kilogram per meter cube. So but for the stall speed, so it is at height of 10 kilometers. So you need to find a table for a density of air at 10 kilometers. So it can be assumed it is around 0.412 kilogram per meter cube. So we substitute in this equation, so we get the value of V is equal 50 meter per second. So the power, the equation is drag force times velocity. So the drag force can be calculated by using this equation. So and then the velocity is the cruising velocity, which is 80 meter per second here. So and then we could get the power is around 13,700 watt. So and then if we have 45% of the power is needed to move the airfoil. The power required at a cruise, if 45% of the power is needed to move the airfoil, so means that the idea is actually the 45% here is the efficiency, So it is equal to the power out divided by power in. So we need to supply more power because a part of that power is used to move the airfoil. So, and then P in. So P in is actually the power required. So it is around P out divided by 45%. So we could get it is around 30,400 watt. So and then the CD here is actually the common CD at this situation for conventional airfoil. So this is what that we have here. So this is the angle of attack. So this is the lift coefficient. So and this is the drag coefficient. So this is another example. So the idea is the lift and the angle of attack. So the bigger the angle of attack, so you may increase the lift force, but at certain point a stall happen. So stall means your object, your airfoil may be lost its lift force. So then it maybe cannot continue to support your flight. So your flight will lose ability to fly. So this is a very critical point. So for aeronautic engineering, they are very alert about this one. So and then it can be caused by another reason, another cause, for example, the icing, the formation of ice on the wing also could create a stall at lower angle of attack. So we have here, so we have the specially designed airfoil, and this is the conventional airfoil. So normally for special design airfoil, so you will have the CL over CD ratio is bigger compared to the conventional airfoil. It is to help your flight, your aeroplane to get more lift force with a lower CD. So this is the example 5. A proposed aircraft is to resemble a huge airfoil flying a wing as shown below. Its wingspan will be 200 meters and its chord will average 30 meters. So estimate, assuming a conventional airfoil, the total mass of the aircraft, including payload, for a design speed of 800 km per hour and at elevation of 8 kilometers, and also calculate the power requirement. So this is just to extend our knowledge about the calculation of lift and drag force. So the wing is delta wing. So you could calculate, you could search about the delta wing. So it is a wing with a triangular shape like this one. But to simplify our calculation, it is okay for us to take the wingspan of 200 meters and the chord is around 30 meters. So we could calculate in rectangular shape. So let's say it is a conventional airfoil. So from figure 8.13, we could assume that CD over CL, it is 47.6 and CL lift coefficient 0.3. So and then we could calculate the mass, okay, by equating the CL here 0.3 with the lift force and the 1/2 rho AB squared that we have. And the lift force here is actually can be reflected with the mass times the gravity, and then we could calculate the mass is actually 2.38 times 10 by the power of 6 kilogram. So and then we could calculate the power Fd times velocity. So we could calculate the value of Fd here. So by using the CD, so CD is given here. So we could calculate by 0.3 SCL, and then we could get the CD. So finally we could have around 490,000 watts. So and then it is equal to 657 horsepower. So means that the power required to the aircraft is around 657 horsepower. Now we continue our discussion about boundary layer. So we see another tutorial. We have question 1 here. A timber is pulled by a boat along the river with force 200 Newton as shown in figure 1. On the half of the timber above the water, determine the drag force due to front surface of the timber. And from this question, it gives us density of water is 1000 kilogram per meter cube. So, and then the dynamic viscosity of water is 1 times 10 by the power of minus 3, or you can assume it is 0.001. So assume that laminar boundary layer is fulfill the Blasius assumption. So mean you could use Blasius equation to solve the fully laminar boundary layer, and you could use 1/7 power law if the condition is fully turbulent boundary layers. Okay, let's we see the question. So the question asks to find the drag force due to the front surface of the timber. So the front surface of the timber means you need to calculate the drag force due to this surface. However, the boundary layer is actually occur at this surface. So what you should understand here is if we have one object, for example, a timber here, so the frontal area here will give you a drag resistance. So at the same time, the boundary layer occur at the surface here is also give you a drag force. So in this question, the total force of boundary layer here and also the drag force according to the front surface will give us 200 Newton as a total force. So another thing that you should see in this problem is you will find that the boats move with speed of 2 meter per second, and at the same time the river flows at 1 meter per second, and the direction of flow is not the same, so they will flows in reverse direction. So in this situation, what you should do is you should create another situation with which the timber is fixed and the flow is moving at certain velocity, because the direction here is on the different direction. So so we need to add the velocity. So we could create a situation where we have a timber here static, so mean the velocity is 0. However, the water flow will become 3 meter per second. So this is the idea of relative velocity. Okay, let's say if our calculation is fully laminar, so we could use the drag force from the Blasius solution, and if it is fully turbulent, so we could use a drag force for fully turbulent based on the 1/7 power law. So first we need to calculate the Reynolds number at the end of the timber. So we use the equation of rho u at over mu. So we substitute the value. And we use velocity here as 3 because they flow in different direction. So and then we get it is 3 times 10 by the power of 7 here, so means that the Reynolds number is the turbulent. So and then we need to determine whether the length of laminar boundary layer is significant to be counted or not. So the critical Reynolds number is 5 times 10 by the power of 5. So the equation is rho u x over mu. So we could calculate the x here, and we could get x here is equal to 0.15 meters. So because the timber here, it is 10 meter long, so means that 0.17 meter here is less than 10%, so it is very small. So we assume that it is okay for us not to take laminar boundary layer into our calculation. So laminar boundary layer can be ignored. So the drag force can be calculated by using this equation. So we have a drag force equal to CD 1/2 rho u square A. So A here is the cross-sectional area. A is actually the A that react with the shear force, where the shear force acts on a surface. So here we found that we have a timber here. So however, the water level is half of the timber. So means that we need to calculate what is the area of this one. So we could calculate it as 1/2 times 2 pi r and times L. So we get it is around 6.286 meters square. So we substitute into this equation, we get the drag force due to the boundary layer is 65.1 Newton. So we could imagine that the boundary layer that occur at this area will give us 65.1 Newton, means that an extra force is actually occur because the front surface here. That's why the boat needs to pull the timber with a 200 Newton. So we could have a very simple calculation like this one. So the summation, the sum of a 65.1 and X here, the force that the drag force that occurred due to the front surface. So we found that the drag force at the front surface is around 134.9 Newton. So let's say we see another question. So let's say figure 2 shows a flat plate 3 meters length times 1.5 meters wide. Moving at 5 meters per second parallel to its length, determine the power required to overcome the drag. So now in this question, they asked to calculate the power. That we could take rho is 1000 kilogram per meter cube and mu is 0.001. So again, first we need to calculate the Reynolds number at the end of the plate. So we use rho ux over mu. So we substitute the data. So we get it is 1.5 times 10 by the power of 7. So it is fully turbulent. So and then we check the value of laminar boundary layers distance. So the critical the critical numbers is Reynolds critical is 5 times 10 by the power of 5. So we could find that the X of lamina here, it is equal to 0.1 meter. So because the total length is 3 meters here, so and then 0.1 meter is very, very small. It is about 3.3%. So we could ignore the effect of laminar boundary layer. So because we assume it is fully turbulent, so we could take the CD here based on the 1/7 power law. So it is 0.074 over Reynolds number 1/5. So we get the value of CD here is 2.71 times 10 by the power of -3. So we substitute into this equation. So we could get it about 152.4 newtons. However, this value is actually the drag force for one side. So because we assume that we have a thin plate here, so we have a boundary layer at this area. At the same time, boundary layer also occur at the bottom surface here. So means that the drag force should be times 2 because it occur at two faces, two surfaces. So the total of drag force is 304.8 Newton. And to calculate the power here, so we multiply the drag and the velocity, so we get it is around 1524 watts. So we go for question number 3. So we have water at 20 degrees Celsius at 1 atm, flows at 2 meters per second, past a smooth flat plate, 1 meter long and 60 centimeter wide. So we need to estimate the trailing edge boundary layer thickness, which is delta, the trailing edge wall shear stress, so which is tau, and the drag force of one side of the plate. So, and then it is given that the fluid is water, the density is 1000 kilogram per meter cube, and mu is 0.001 kilogram per meter second. So first we calculate the Reynolds number at the end of the plate. So it is 2.2 times 10 by the power of 6. So it is turbulent. So and then we need to calculate the critical Reynolds number. So we found that the critical Reynolds number is, let's say, the common one is 5 times 10 by the power of 5. So we found that the L, mean the length of laminar boundary layer, is around 0.25 meter. So which is 25% from the total plate. So means that we need to consider the laminar boundary layer. So this is assumption that we use. So for laminar boundary layer, it is okay for us to use the Blasius solution. And for turbulent boundary layer, so we use 1/7 power law assumption. So first, I think you still remember. So we have a plate like this one. So and then we have a laminar here, and that it start to become a turbulent. But this point is actually not the starting point for the turbulent. It is virtually the turbulent is maybe start at this point. So we need to calculate what is the distance of this one. So this is actually the major idea of this calculation. So however, so this point, okay, this thickness is actually delta, mean the boundary layer thickness. So it is shared. It's shared by the turbulent and also by the laminar. So we use this idea to solve the problem. So means that this is the delta. So we could calculate the delta by using the laminar boundary layer. So based on Blasius solution, so we have 5x over square root Reynolds critical. So we substitute the Reynolds critical here is 5 times 10 by the power of 5. So we get it around 1.768 times 10 by the power of minus 3. So and then this height, this thickness, okay, delta again, we equalize with the equation of the turbulent boundary layer. So we take 1/7 power law. So the turbulent boundary layer, the thickness here, okay, can be calculated here, and then we found that the value of x1 mean here this is the distance of x1. So the distance of x1 is 0.066 meters. So and then we could calculate the total length of boundary layer. So mean the total length mean the length from the origin of boundary layer, the origin of turbulent boundary layer until the end of the plate. So the distance here can be calculated by the idea of 1 minus 0.25 plus 0.066. So 1 is the total length from here to here. So and then 1 is here to here. So and then we minus with 0.25 mean the length of the lamina, and then we add with extra of 0.066. So mean that now we could get the total length from the virtual starting point of turbulent boundary layers until the end of the plate. So means that if we separate the lamina and turbulent boundary layer, so turbulent boundary layer can be imagined start turbulent boundary layer here, let's say. So the length of this one is actually 0.816 meter only. So that is the idea of this calculation. So and then because after this we need to calculate the thickness at the end of this plate here. So and then it is okay for us to use only the turbulent boundary layer, but be careful, we need to use the right distance, mean the distance from here to here. So for we calculate the Reynolds turbulent boundary layer, so rho UL over mu, so we substitute here as 0.816, so we get it is 1,632,000. Okay, so and then the boundary layer thickness at the edge here can be calculated by using the equation of this one. So this is the equation for the boundary layer thickness for turbulent boundary layer. So we substitute the x here with the 0.816 meter, and the Renault number here is these numbers. So we get it is 0.0174. So mean that the boundary layer thickness at this range at this location is 0.0174 meter. So again, we could calculate the shear stress at trailing edge. So we use the shear stress from the 1/7 power law boundary layer. So we get this is the tau wall, and as we substitute all the value, the Renault number here is these numbers. So and then we could get it is tau is equal 6.60 Newton per meter square. So next, we need to calculate the drag force for the one side of the plate. So please refer to our previous notes. So because we take critical Renault number as 5 times 10 by the power of 5, so we could use to calculate the CD by using this equation. So we substitute the value. Okay, so here the Renault number for this one and this one is actually the Renault number for the total plate. So means you need to substitute the Renault number of this one. Okay, so the idea is, we have a thin flat plate here. So we have a lamina. So and then we have a turbulent. So and then let's say we have the imaginary origin for turbulent. So for calculating delta and shear stress at this point, shear stress means the resistance. The shear stress occurred at this point. So it is okay for us to use the idea of turbulent boundary layer because we take the correct distance. Okay, so now we could calculate the delta here based on turbulent boundary layer and also the shear stress that occur at the edge of the plate. However, the drag force means the total force, the resistance force that occur on the plate. So it means we need to add all these resistance because of turbulent boundary layer plus the resistance that comes from the lamina boundary layer. That's why we cannot just use the CD here. We cannot just use the CD from the 100% of fully turbulent boundary layer because it is only show this distance. It's not take care about this distance. And also if let's say we change the distance here with the total distance of this plate, so means that our boundary layer is start from here now. So means that we create a bigger range of boundary layer. So means the delta here is not reflect the real situation. So we use this equation. So this is equation that we will use. So this idea is if you see 0.073 is actually the CD for the total turbulent boundary layer, and we need to minus with a certain amount. So this amount is actually the unnecessary part, okay, to reduce a little bit the total value because lamina here only give a small, not so high value of resistance. So I hope you could read this in the previous notes. So we have this note. So and then because we take Renault critical is 5 times 10 by the power of 5. So the CD here is 0.073 over Renault number 1/5 minus 1700 and Renault number. So we get it is 0.00316. So we use substitute in this equation. So we get the drag force for one side of the plate is 3.792 newtons. Okay, so we go for question number 4 here. So figure Q1 shows a uniform flow plus a flat plate. Determine the wall shear stress between AD, mean between this point and this point only. So the distance is 0.5 meters. The velocity profile is lamina, and it is assumed equal to y over delta by the power of 1/2. And given in this question, the the delta means the delta at this point AB is 0.5 meter, and delta for CD is 0.16 meter, and take the density of air as this one, and the dynamic viscosity is this one. Okay, first what we need to do is we need to calculate the shear stress. So according to the von Karman equation, integral equation, so we have the rho u square d theta dx, so we could write as rho u square d over dx of theta here. So theta here can be calculated by using common equation. It's zero to so theta can be calculated by the idea of 0 to delta u over capital U minus u over capital U dy. So we substitute the value of u over u here with y over delta by the power of 1 over 2, and finally we could get it is theta here is equal to 1 over delta, I'm sorry, 1 over 6 delta, and then we substitute this value into this one, so we could get this term. Okay, so for this term, okay, we don't need to integrate it because we need to answer based on the diagram that we have. So the d delta here means the thickness difference. So because the question needs only to calculate the shear stress, not for the whole plate. So we need to calculate the shear stress between AD only, between these 2 points. So means that the d delta here is the thickness difference between that 2 points. So the thickness here is actually this thickness. So we could say that d delta here is delta CD minus delta AB. So it is equal to 0.01 meter. So and then the x here, okay, so actually the distance different. So because we only want to calculate the shear stress between A and D here, so the distance is 0.5, so we could substitute the value of dx here as 0.5. So we calculate all the value here, so we get the tau wall for area AD. Okay, tau wall for area AD is equal to 1.007 times 10 by the power of minus 3 Newton per meter square.